So let's look at the idea of centripetal acceleration, sometimes called centripetal acceleration. Now you might have heard of centrifugal forces, and that is related, but that's not actually what we're talking about here. So we never really refer to centrifugal, we talk about centripetal. And we have to get our heads around this rather strange statement here. And very often exam questions will ask you to explain what's going on here. So an object moving at constant speed in a circle is accelerating. Acceleration at constant speed. This sounds like it's a contradiction, but we have to understand, well, what do we mean by acceleration and what do we mean by velocity as well? So if you imagine we have, imagine an object moving in a circle, then we've got an object here and we have a velocity in this direction, and then the direction changes. So because velocity is a vector quantity, then the velocity is changing. So that's part of the explanation, the idea that we've got a changing direction of velocity. Also, we have a force towards the center, and we'll talk about that in a moment. There will be a resultant unbalanced force, therefore there must be an acceleration towards the center. So it might be a tension is acting towards the center, but there's nothing balancing that. And we need that tension, that resultant force, to change the direction of velocity. So again, if we refer to Newton's second law, F equals ma, if we have a resultant force, we must have an acceleration. And then it's always directed towards the center. So these 3 bullet points here are very often the answer to a 3-mark question in the exam to what is meant by acceleration at constant speed. So very, very important. Now we need to look at as many examples as possible to understand what is providing the centripetal force in every case. If something moves in a circle, then something needs to provide a centripetal force. So if we have a car going around a circular path, around a bend, then there'll be the friction between the road and the wheels towards the center. If we have a satellite in orbit, then the weight caused by the weight due to gravity is providing the centripetal force. An electron orbiting a nucleus, there's an electrostatic force of attraction, which is providing the centripetal force. And we'll look at this next lesson in more detail, the conical pendulum. This is very often the subject for an exam question. So we have an object moving in a horizontal circle, and we have a tension in the string here, and this will provide a horizontal component which gives us the centripetal force. So we need to understand centripetal acceleration and also centripetal force. Fortunately, centripetal force and centripetal acceleration are very, very straightforward formula. Now, some specifications ask us to derive these. On the particular one I teach at the moment, you don't have to derive it, but it might be worth looking into, perhaps. Either way, we're given this in the formula booklet. So F is equal to mv squared over r. So this is not only important for this subject, this is really useful for other subjects as well. Certainly gravitational fields, which you'll be studying soon after this topic. And later on, when we look at orbiting charges, electric fields, certainly magnetic fields, then this is a really important formula. And if we can accept that, then we know that Newton's second law, F equals ma. So if we just look at what remains, v squared over r is the centripetal acceleration. So we could calculate, if we know v and r, the acceleration, and if we know the mass, we can find the centripetal force. So a simple example here, and you might get questions this simple. Certainly at part A of an exam question would just be calculate the centripetal force. So if I know the mass, and I know the velocity, and I know the radius, then I can calculate mv squared over r, and we get our centripetal force. Bear in mind that very often we have to explain or describe what is providing the centripetal force. And as we mentioned briefly a minute ago, if we're looking at a car going around a corner, then by turning the steering wheel, which turns the wheels, that generates an additional friction force between the road and the tyres, or the tyres and the road. So we actually have a Newton's third law pair here. And the one we're interested in is the force acting towards the centre. So that's the friction force of the road acting on the tyres towards the centre of the circle will provide the centripetal acceleration. Let's look at a really typical application of circular motion. So this is a mass moving in a vertical circle. So we've got a ball on a string which is moving in this vertical plane here. So normally we need to consider the forces acting at the top and the forces acting at the bottom. So let's consider at the top. So we always have the weight acting downwards, mg, and we also have the tension in the rope. So when it's at its highest point, the tension is pulling it down towards the center. And at the bottom, slight variation, the weight still acts downwards, but at the bottom the tension is once again acting towards the center, and that should make sense. So the tension on the string is always pulling it towards the center. So we need to think, well, how do these two forces combine to give us the resultant force that we call centripetal force? Now this is really, really important. Very often students get confused and think that centripetal force is another force which appears out of nowhere as if by magic. It's not. It's just the name that we give to the resultant force which arises out of the existing forces. So there's only two forces, the weight and the tension, but at the top they combine together. So mg plus t will give me the resultant force. And we can see at the bottom then the tension and the weight are acting in different directions. So the tension has got two jobs to do now. It's got to balance the weight and also provide a resultant centripetal force towards the center. So Fc, the resultant force, will be T minus mg. So this is really important, the idea that the centripetal force is the name we give to the resultant force which arises out of the existing forces. And then either they combine together or it's T minus mg at the bottom. So we can see here that at the bottom, because the tension has got to overcome the weight and still provide a resultant force, then the tension is going to be largest at the bottom of this vertical circle because it's got these two jobs to do. Let's look at one final example in this video, and then the second video in the series we'll look at several more examples and some more difficult scenarios as well. So this is Ferris wheels. So as I said at the start of earlier on in the video, you need to consider as many different applications as possible so that you are confident with understanding what the forces are, which direction they act in, and how they combine to make the centripetal force. So let's have a look at a Ferris wheel. So at first glance it looks very similar to the previous example, but it is slightly different. So let's have a think about at the top. So the weight always acts downwards, that's fine. Now we don't have a tension pulling us towards the center as we did with the object on a string. Now because we're moving a lot more slowly and because there are people sat on chairs, then if someone's sat on a chair, then there's a reaction force acting upwards of the chair on the person. So that's actually acting upwards rather than the tension acting downwards. So that's slightly different. However, at the bottom, while the weight always acts downwards, the reaction force is still acting upwards. So actually at the bottom, this looks very similar to the object in a vertical circle where the tension was acting upwards. So this is one of the challenges, and why you need to be really confident with lots of different examples, is there are some similarities, some differences, and very often students get extremely confused with what the forces are and in which direction they're acting. So the resultant force, which is the name we give for the centripetal force, at the top is equal to the weight take away RT, the reaction force at the top. So that's slightly different to what we had before. If this was the tension, it was tension plus mg, because the tension was acting downwards towards the center. However, at the bottom, that looks very similar to our previous example. The reaction force has got two jobs to do. It's got to balance the weight and also provide a resultant force towards the center.